we're going to talk about control loops. I've created a folder here with all these points, which you'll go ahead and pause if you have to and do all this. We'll do 3 control loops, a proportional integral, a reset, and a trim and respond control algorithm. So the first one we'll talk about is the reset. If you go to your library under math, linear fit, basically just the returns the y-intercept based on the x value, so it's the slope intercept. Save it. So yeah, I think it's actually very efficient to put your control loops in a function and then call those functions or declare instances of those functions and call them from a program that's actually controlling a piece of equipment or a subsystem inside a piece of equipment. So we will need the hot water supply temp, and it has to be an input. OA temp. And since our function is not controlling for the lowest possible value or highest possible value, then we have to put that control in place in the program. There's likely a way to enhance this function with a function that clamps the low and high limit values. You'd probably need an extra set of arguments to specify. Actually, you probably wouldn't. No, you just use y1 and y2 as the limits. So that would be a very neat way to enhance this function that you get by default with the editing tool. So, but for now, take the largest of these two. In order to make sure that our output value never goes below 120. And then we'll take the smallest of the two to make sure that if our output ever goes above 180, we take the smallest of this, so we would take 180 at that. In that instance, if our output turns out to send a set point of 200 degrees, well, we don't want that, so we'll take the minimum of the two. We'll take 180, and then we call the function so OA temp is our x value. Then we'll have 10. Let's go with 55. 180 and 120. Okay, so now let's go ahead and do some binding. Save. Okay, so at 55 degrees, we're at 120. Let's make sure we don't have any runtime errors. So as we've talked about before, runtime errors don't show up when you try to compile. But they will show up when you're debugging. So let's add another line here. I do this in order to keep control or assert control over how fast this program executes. So So this is 0 because it's not being used by the program. So structure_var has this thing where if it doesn't use the variable, it doesn't update the value in the program, that is. So let's go ahead and change this to 10. Alright, we have 180. So this seems to be working. Real good. Alright, so the next one we're going to look at, it's going to be how to make a trimmer respond. And why would we use a trimmer respond? So, well, we've seen how our resets are good for like proportional output, an output that's direct. There's a mapping between two values or two schedules of values in order to create an output that's proportional to the input, basically. So it'd be used in things like outside air temperature to reset your hot water supply temp set point, or using terminal load, average terminal load for all the VAVs to reset the supply air temperature set point, things like that. They use reset blocks or reset functions or linear fit, however you want to call it, or slope intercept. So the trimmer respond, one very common application and very well documented would be for controlling the supply or resetting the supply air pressure set point in order to get all the VAVs to open as much as possible to deliver the design airflow with the lowest possible supply duct pressure. So right now, most buildings that don't implement this measure, they will control the supply air duct pressure to a static 1.5, for example. But a lot of VAVs at this 1.5 inches of water pressure, they might close all the way down to 5% at minimum flow when there's no load, no thermal load in the space. With this trim and respond control loop to reset down or trim down the supply duct static when there's low load or very light load in the building, you achieve even more savings and you maintain minimum design flow, and you make sure your VAVs are wide open, because if they're closed, then they're just making the fan work harder for the same amount of flow, that is. So let's take a look at that. Alright, so here are function arguments. Alright, so let's looks like this is the longest name. So what is the output value? Is a local, let's make this larger. So local variable to store these functions. Functions final return value. What's the low limit? So bottom of this scale. Our PVs are process variable, our sensor essentially. So our sensor is our control parameter, set point. Our set point, control parameter. Our control variable false. Function is just a pass through for the CV trim to add or subtract when control action is required. And our high limit is basically high end of the scale. You have to debug nesting issues. It gets ugly. So basically we're saying here, if we're enabled and if our CV, our control variable, is more or equal than the low limit and it's less or equal than high limit, then we can go on and do what we need to do to adjust the output value or our set point. If not, if we're disabled, if this control loop's disabled, or we've already calculated our way above or below the high and low limits, then we're just going to act as a pass-through, and we're just going to say output val equals CV. So the same CV that you get is what you end up returning out the function. So now this is saying if our process variable or our set point, but our sensor, in this case it would not be a sensor, it would actually be the max or the average. You'll have to play with those values, the maximum or the average. In this case I'm doing the maximum because it's easier to debug, of the zone damper positions. And our set point is going to be, for example, 89 or 85%. We want our dampers, all our dampers in the whole building, to be at 85% because we've determined that's going to be the most cost-effective place when there's very little load, in order to maintain minimum design flow. Now you'll notice that you'll have rogue zones that will have a harder time getting satisfied and making it to 85%, where every other zone in the building will. Well, you can adjust that. That's why you have 85. Ideally you want every zone at 100, but that's gonna be pretty much impossible. So 85 is just kind of where you start, and you may be able to get more out of your system. You may be able to get all your VAVs with no problem at 92%, and that's great. But if you can't, don't be afraid to go down with that set point. So CV plus the trim. So we have a zone damper here of 82.5. Yeah. So, all right. So, if not, if PV is less than set point minus the deadband divided by 2, then output val equals CV minus the trim. And this is just to make sure that our loop is never going to calculate above or beyond, above or below unreasonable values, or reasonable values, I should say. So and then CV, and that's that.